Well, thank you, Stefan. As you've mentioned, I'm Mike Thompson, formerly of Procter Gamble. As of October 1st, I've retired. In this talk, the Bayesian Networks for Recommender Systems, we're going to go beyond ratings, predictions, and use the most relevant explanation feature within BayesiaLab. This is work that I've done with Javisha Anand, Masters of Science for Business Analytics at the University of Cincinnati in the Lindner College of Business. I teach a special topics course there in Bayesian Analysis. I was a reader on her capstone project for her degree. So this spurred the interest. Here's the outline, and I won't read through all of these, but it should be a relatively brisk presentation as we go through the recommender system and focus more on the extraordinary things that I think Bayesian belief networks bring to the problem as opposed to performance of the recommender system, etc. So, as I mentioned, this was something initiated by Javisha in her capstone project. And the idea was to take a case profile, which involves the viewer attributes or viewer feature, movie features, in this case specifically just the genre of the movie, no other information like director, star, or anything like that, or year, but only the genre of the movie, and then the past ratings. And this is, if you're familiar with the Movie Lens database, this is the small version. You can download it from Kaggle.com or many other places, but it's the smallest of the Movie Lens versions. And out of that, we get recommendations, which is a ranked list of movies. And I intentionally left this small and illegible because we're not going to focus so much on the actual recommendations as the construction and some of the BayesiaLab features that I think are really unique, that the lab brings a special power to this. All right, so our approach was to build a Bayesian network, tree-augmented naive Bayes network for every single movie in the database. And I forget the number of movies, a couple of thousand movies were in this database, I believe. And rather than another approach would have been to just throw all the movies in and use their 5-level ratings score as the states of the nodes, build that giant BBN. And you can imagine a recommender system then that would have some nodes. But then when you throw in the content information and the viewer features, you would have a sprinkling of just a handful, or maybe at most, say, 20, 30 nodes amongst those thousands and potentially even millions in other recommender systems. So you're basically picking your poison between then having those very sparsely connected to only a few movies and losing their predictive power to other movies, or you'd have to connect them all up to many different movies. And then you have these giant cliques, which when you do the inference and forming a junction tree and doing message passing, etc., that would be intractable, and you'd have to do either approximate inference or some other. Also, it's very unwieldy to do all these ancillary analyses that I'll show that we do here, such as audience analysis. So what we do is basically identify movies that are strongly confirm or refute the hypothesis that someone would like the target movie. Talk a little bit more about the following slides. And we hook those up to form the tree augmented networks structure. So the green nodes are those other movies and their ratings. Red nodes are the genre of the movies, and the blue nodes are just the 3 feature of the viewers, which are age, gender, and occupation. Now, for every movie, including the target, we center them on each viewer's median rating. So before building the network, we laid all of the ratings back to giving them a 0 if it's at the median of that user or that viewer, and a +1, et cetera, if you're above, and -1, et cetera, if you're below. Another nice thing about this is it's trivially parallelizable. So we use parallel processing, just go at it and just build all these networks. Big question then is, how do we decide then which are the movies or the candidate movies are going to be in each network for a target movie? Here we use the generalized Bayes factor. The formulas are given here, but the basic idea is simply that if a candidate movie's rating is a strong confirmation that a user would like the target movie, then that movie is high on the list of being added into the network. And I believe the cutoff was 10 candidate movies. The top 10 would go in. But we also, GBF, if you take the log of it, you get the quantity called weight of evidence. It's termed by Alan Turing and I.J. Good when they worked on code breaking in World War II. And they also came up with the units of decibands, which I'll talk about a little bit later. But in that space, now you have a symmetric, where zero being basically no real information, whether confirming or refuting. But if you go negative, it's strongly refuting the proposition. So someone would, if they really like the candidate movie, they'd probably certainly hate the target movie. And what we do is take the absolute value of that. So we throw in those movies that are disproportionately either liked or hated to their predictive ability for the target movie. So if you like that candidate movie, you'll either strongly like the target or you'll strongly hate the target. In other words, they bring a lot of information. So just to illustrate graphically, here, suppose your target movie is movie A and your candidate movie is movie B. Pattern, solid pattern if you like A, hashed pattern if you don't like A. And similarly for movie B, we use green, the color green if you like movie B, and color red if you don't like it. So in a hypothetical set of 1,000 viewers, let's say 600 like both, 200 like A and don't like B. So to find the prior odds, you simply ignore what they thought about B and only look at whether they liked or disliked or were not a liker of A. And I say not like, meaning you either saw it and disliked it or you didn't even see the movie. So the prior odds then, in this case, are the 800 on the top divided by 200, and you get a ratio of 4, which is pretty decent. 80% of the people like the movie. But when you condition on them liking B, you ignore the not liked and you focus only on the green, 100 over 25. So now the odds have increased greatly by a factor of 6 to 24. And so it's said that observing that someone likes B is strong confirmatory evidence for the hypothesis that they'll like movie A. Therefore, candidate B is a good candidate to put into the network. Now, as you notice, these are all just counts. This doesn't involve actually using the network yet because we're selecting nodes to go into the network. So you rapidly go through the counts. But as usual, same with building the conditional probability table in a BBN, you have to account for the fact that you can have zeros or the sparsity of the data. And so we actually, in practice, the computation uses Laplace smoothing, where you add some pseudo occurrences to each state and smooth it slightly. So after we've built a tree-augmented naive Bayes network for every single movie, we then perform inference by asserting the case profile. In this example, it shows asserting all values, the viewer features, the liking on different ratings, and also the fact that they've seen the movie. In other words, the unseen state gets put to 0. So we're asking the question, given this profile and that you've seen the movie, what would the posterior distribution be on the ratings and the rating difference from your mean value? We conservatively use a score. We take the lower bound of the 95% credible interval because for some of these distributions, the posteriors are very broad. And I'll also talk a little more on that because we have this fight between the scarcity of data and we have a bias in the sample set too. But suffice it to say, this is also trivially parallelizable problem. So the inference on every single movie can be done simultaneously. And then we get out the ratings based on the score, the ranking based on the score, and that provides us with the recommendation. The case profile is described at the top. Female doctor, aged between 33 and 44, like science fiction. And like the movies, I forget what, I think this is Star Trek Home Country and Star Trek Generations in years 1991 and 1994. It gives a list of recommendations. It's scored by how many points above their median would we like that movie. This works real well, but there's a couple of issues. It benefits greatly by Bayesian networks being able to quantify uncertainty and capture the fact that we don't need to have viewer features, movie features, or ratings. We could give a recommendation just on the marginal of all the networks, or we can assert any combination of these. But some of the issues, though, again, are we have a sparse data set, is relatively small, and it's biased in that it's very much reflecting sort of a computer scientist on a college campus type of population. So we hypothesized what would we need to do if we wanted to apply this to a broader population like the US population. So we addressed that issue. The issue is the sparsity. For sparsity, we leverage the posterior and just be conservative on that rating suggestion of the lower bound on the 95% credible interval. And when you think about that, that's really when we say we recommend this and think you'd score at 1 star above your median, we're more than 95% certain that movie's there. So we're really about giving stuff you like, and it would be very unusual for us to recommend a movie that you didn't like very much. It's a low probability. Alternatively, and actually, we do some level of aggregation of the states. So we've tested combining all the ratings into just, if you're at the median or above, then it's like. If you're less, it's dislike. Binary, augmented with the unseen state. And then also different prior distributions on the conditional probability tables. I'd really like to explore a full multi-level Bayesian model to use. So for example, if you don't have many female 33 to 44-year-old doctors, at least you can learn from the fact that she's female and she's a doctor and she's in that age range as separate distributions form the prior on the rating scale. We haven't explored that, but that's the next frontier, if you will. So bias, then, we address it using post-stratification. And if any of you are familiar with Gelman and Hill with their multi-level regression models, and Gelman has popularized MRP, multi-level regression and post-stratification, this is the same strategy. We aren't doing the multi-level modeling. We're doing a Bayesian belief network for the model to capture the behaviors of each cohorts. Then, given those behaviors, we're post-stratifying over a distribution learned from the U.S. Department of Labor or Bureau of Labor Statistics. And I'll go into a little more detail on that. First, just again, illustrating the lower bound on the 95% credible interval. That's what it would look like in this case. You can see how broad that distribution is. So there's not very much information at all about a particular case. Now, as far as with the bias, TAN-B is a joint probability distribution of all the aspects of the case profile, the other movie ratings, the movie features, viewer features, and the rating of that particular movie, or technically the delta relative to the viewer's median. That can be factored into the conditional probability of those things given the viewer features times the joint probability distribution, or its joint marginal on the viewer features themselves. Now, our assumption is that we've learned these viewer preferences in a non-biased way, and that a doctor in this sample data set behaves like a doctor in the general population, and we can trust that. It may be uncertain in the sense that we might not have a big sample of doctors, but we don't expect some bias there. Where the bias comes in is the distribution on the people are very different. And this slide just shows that on the top, we have the movie lens sample. On the bottom, we have the population that's gotten from the basically census data. And you can see the age, the gender, and occupation distributions. Age is quite different, especially at the high and low ends. Far more males in the movie lens sample. I believe on the population sample, this reflects both death of males and also incarceration of males being higher. And that's why females has a big enough gap like that. And you can see there's quite a big difference on sample of population of occupations, especially on programmers, and the sample is highly biased. So what we've done is take the U.S. Bureau of Labor Statistics information on occupation, gender, and age, and built a small Bayesian network on those three variables and connected it into the TAN-B to augment it. So we put a new node called distribution source, whether you're from the movie lens sample or whether you're from the population. Then we assert evidence saying we're looking at the population and use BayesiaLab's really powerful feature, evidence instantiation. And I'd like to brag again about the time at Procter & Gamble. This is a feature that we suggested they add to BayesiaLab, and it's been a real powerful feature so that when you use this feature, it generates a new network for you. So graphically, to illustrate that, we've added this. Note we had to change the arrows here to ensure the exactness and connect here so that we would have the types of clicks necessary to reverse the arrows back. But some of the technical details, more important thing is that this is a very feasible and automatable process. So we add that additional node in. Then we assert evidence on that node to the population, and that changes all these distributions. They look just like the graph I showed for occupation, age, and gender. And we go to tools and evidence instantiation in BayesiaLab. So what that does is turn for you a new neural network, a new Bayesian belief network that reflects exactly the distribution according to that evidence. So now we're back to 100 joint probability. There's no asserted evidence on any of the nodes, but their marginal distributions are exactly those corresponding to the population. So now we've basically done, in essence, a transfer, or Elias Berenbaum of Columbia University would call this transportability. We've transported what we've learned from one sample and context to the other. Classic post-stratification strategy. That's how we dealt with the bias of the sample. The final thing I'd like to show is how, because we're in this consistent Bayesian probabilistic framework, and we have the joint probability distribution of literally everything defining the universe we're interested in, use that same model, that same ensemble of models for all sorts of analyses. So we could take any movies can be, do an audience analysis to find the folks who are really likely to love that film. And I'll show how we use BayesiaLab's most relevant explanation feature to achieve this. And now we're using a generalized Bayes factor, but the evidence fixed is that we would like target movie of interest for which we're trying to find an audience. And then we're going to have BayesiaLab search over all combinations of viewer features in gender, age, and occupation so that as to maximize the score and find the viewers who have a higher prevalence amongst those viewers of liking the movie. Written as posterior odds over prior odds, it looks like that. And I'm using the convention that if I put an asterisk on a quantity, that's the fixed quantity, and the search is over the non-astricized quantity. So we fix the evidence saying we like the target and search for all the hypotheses. Both the numerator and denominator are changing. Alternatively, we could have done it this way. I've come up with this term, most confirmatory clues, where you fix the hypothesis and search over all the sets of evidence. In that case, the prior odds in the denominator would be fixed. You're really searching for ranking them by posterior odds, which is monotonically increasing with the posterior probability. For a simple one node hypothesis like this is equivalent to using target optimization. And I've tried that in BayesiaLab, used the target optimization, allowed for some of the candidate nodes to not have evidence asserted, and it returns the same quantities I found in writing a separate algorithm to perform this. But I'll talk about features we'd like to see in BayesiaLab. And one of the things we'd like to see is that you could use any arbitrary compound hypotheses here. And I'll go into that a little more on the later slide. So what that looks like then is we assert the evidence that we like the movie. So we exclude any ratings less than the median rating for a viewer. We exclude being unseen. So they have seen it and they even gave it their median or greater than their median. Then the BayesiaLab go analysis, report, evidence, and most relevant explanation. That will return out a report that finds all the combinations of, in this case, we were searching over the selected nodes of age, gender, and occupation. Now, focusing here, what I've done is take the report from BayesiaLab and put it into Excel, because you find that it returns a report in its standard form that has, I believe it was 94 different combinations of age, gender, and occupation. This was, look at the dialogue, I'll not show that, but if you look at the dialogue for the most relevant explanation, BayesiaLab, you can allow a certain amount of filtering where, for example, the simpler hypothesis relative to the first one, age and occupation versus age, gender, and occupation. If the second one had either the same or higher weight of evidence, then we wouldn't even show the more complex hypothesis. We'd only show the simpler one. This filtering level 1 that we're using to generate the report. There are a couple of issues. So this had, like I said, some 90 something. And I'll talk about these 3 issues and lead to my suggestion for 3 new features. So one is Cass and Rafferty had pointed out, be a threshold under which substantial support. And by allowing in the dialog box someone specify what a threshold is, the nominal one is actually 1.66. Here I'd set it slightly lower to see what the tail end looked like, not show any more than that. And that knocks off another like 30 different hypotheses not show up. Second one is the discernibility that IG Good points out. It's 1 deciband or about a third of a bit. By here, I've quantized the weight of evidence. So now instead of 3.5 and 3.4, you see that they're within same quantum of 0.33. So really, they'd be roughly the same. And since the 2-node or two-term MARI is simpler than the 3, we would really just want to see engineers in this age range and not be concerned about gender. So another way of focusing on what's really a significant difference. Finally, we're looking over posterior odds divided by prior odds is the definition of GBF. But sometimes, so you can have really tiny prior odds, and even though the posterior odds could be 10 times more, you're still at really tiny posterior odds, and therefore posterior probability, and therefore very small joint probability of that hypothesis and evidence. And what that means is it might only refer to just a few people, like 63,000 people out of more than 300 million people. And so in that case, we would like to be able to set a threshold. I use a nominal one of like 0.3%, that we're not just into the noise of what the model has and can try and avoid that. By imposing those 3, so in Excel, I created a column that true or false, whether we satisfy the 3 conditions. By filtering on just those features, we end up with a much more concise analysis, and we get a nice tight report on just 8 hypotheses. Here's in this age range, and this is consistent in that the data set was collected, I think it like around just late 90s, and that movie occurred in 79, Star Trek, and so finding engineers in this age range where the most likely audience for it is very consistent with all the information. So then the final 2 slides I'll show are simply the potential extensions. One, adding that most confirmatory clues. So instead of seeing evidence and searching over hypotheses, which MRE does, the hypothesis search over the evidence. And it differs from the target optimization in searching for or maximizing a posterior by generalizing H so it can involve multiple nodes with soft or hard evidence. And so it makes it just more flexible. Allowing the thresholds, the 1.66, allowing thresholds on the joint, which would be like the 0.3%. So allowing that tolerance, the 1 deciband quantization for comparison. Then finally, one thing I found sometimes, especially I built a tool and talked about a few years ago, for college selection for my daughter, one of the things I wanted to do is say, well, what are the features or the groups that are really alienated or strongly refute the hypothesis? And that would be the least relevant explanation or the least confirmatory. So simply allowing to do a minimization as well as a maximization. And I'll take this up with Lionel and we'll see if we get any traction on these features. So to conclude, the analysis over the entire joint probability distribution is a really powerful feature of BBN. It's everything consistent and you're not doing all these ad hoc types, both analyses and algorithms to achieve what you want. And that's very different from using this collaborative filtering and hybrid content-based plus collaborative type recommenders where to do this audience analysis. So for example, I forgot to mention one of the motivations for the audience analysis is to drive more revenue for a company in that you can then turn the ratings into marketing dollars by finding specific audiences that you can then sell to either other sponsors or you can market things to directly yourself as a company and generate more revenue. And we've done that all in the same context of built the one model building's done, and now we just use that joint for everything. But a caveat is you have to avoid racing out into the tails. You have to put in lots of measures so you can retain some robustness. Finally, the second thing is that because it's a Bayesian probabilistic framework, it's all principled allowing post-stratification and uncertainty quantification. But if there is huge bias, so one of the issues here is that data set is 20 years old. And so I used the population distribution from 2019. So the assumption is that, say, a person of a specific cohort will have the same preferences. Obviously, that wouldn't hold 20 years later. But there's things like that. There's only so much you can do to try and overcome selection bias. Contextual issues like that are not addressed by the post-stratification. Then if you just have really sparse, extreme sparsity, no amount of this is going to, there's no free lunch in the information theory sense, theoretic sense. You're not going to get more information. And the most thing is always, BayesiaLab is the state-of-the-art in Bayesian analysis. It has capabilities that are far more powerful than anything else. Yet I'm going to keep on Stefan and Lionel to add new features. Finally, questions.